In this video, we're going to use the one proportion test, the one prob z test, on our TI-83s. Whenever you're dealing with a proportion, you're going to end up using this test. So in this example, at one time, Sprite claimed that 1 in 6 of their 20-ounce bottles would win a free soda. You think that their claim is too high, so you're going to challenge the claim of 1 in 6. Imagine that it's reasonable to assume that buying a soda twice each day for 2 months constitutes an SRS of the population of Sprites. In your sample, 19 of the 122 bottles were winners. So you took a sample, consider it an SRS of 122 bottles, 19 of those were winners. Do you have enough evidence to side with your hunch that you think that less than 1 in 6 would win? With proportions, you always need to check a few assumptions first. You always need to look for 10 successes or more, 10 failures or more, and you have to make sure that you're pulling from a large enough population. If your population is too small, it's going to skew your results. So in the first example, 10 successes, we have 19, so no worries. 10 failures, we have over 100 failures, so we're good there. And a population at least 10 times our sample size. That means that the population of all Sprites should be more than 10 times this number, so more than about 1,200. I would say there's probably more than 1,200 bottles of Sprites out there, so this population should be plenty big. The null hypothesis is always a statement of no difference, or of supporting the claim. In this case, Sprite claims 1 in 6 are winners. So the null hypothesis is that P, since we're dealing with the proportion, is equal to 1 in 6. The alternate is that you think that it's less. You think their claim is too high, so you think the actual answer should be lower than 1/6. So P is less than 1/6 is your alternative hypothesis. Now, your number of successes is called X, so that would be, in this case, 19. The N, or the total number in your sample, is 122. If you remember, with confidence intervals, we had a +2 +4 rule for proportions. That does not apply to a test. So when you're doing a proportion test, a one-prop test, you do not add 2 successes and 2 failures to your data. You just leave it as it is. What you'll do from here is you'll take out your calculator, you'll go to Stat, you'll go over to Test, and one prop Z test is a little ways down here. And you'll notice all the values deal with things like proportions. So it says P equals, in this case that's going to be your null hypothesis. You can just type it right as a fraction. Your calculator will take care of doing the division for you. Number of successes, X, is going to be 19. Number in the sample will be 122. And we are doing a one-sided test where P is less than 1/6. So it looks like I've got the right one selected here. It's that middle one. And we're going to calculate. And here is the data that we get. Our p-value is 0.37. And so we usually should have talked about picking our alpha first. In most cases, we would just assume that it would be 0.05. But 0.37 is way more than 0.05. It's nowhere close. So given that it's a long ways off, we're going to assume that we cannot reject this. We don't have evidence. And just to show you that visually here, I'm going back into the test and I'm clicking the draw button. And you'll see here that this curve is mostly shaded in. 37% means that we're shading in the area almost all the way up to the sample mean, or the sample proportion, or the null hypothesis, excuse me. And what we're seeing from that is we don't have very good evidence at all to reject their claim. In fact, our data almost supports their claim that our data ends up being so close to the null hypothesis. So we are not going to be able to have the evidence to side with our hunch. In another example here, we have a national poll that says 41% of Americans approve of the president. You think that it's lower in your town, so you conducted an SRS of 90 people in town. 31 of them approved of the president, so 31 out of 90 approved. Is your town statistically significantly lower? What we're trying to prove here is that one population, which is your town, is different than the larger population, which is the country. So there's a statistic about Americans, and you want to see if that statistic applies to your town too, or if your town is actually different than most Americans. And so what we're going to do is always start with our assumptions. Do we have 10 successes? Yes, we have 31. Do we have 10 or more failures? 31 out of 90 means we have almost 60 failures. We're good to go. Is the population 10 times your sample? Well, if we have 90 in the sample, then we would have to have at least 900 people in town. And as long as you're not in a very small town, that should be fine. Now, the null hypothesis is, because we're dealing with a proportion, is going to go with the claim, the national poll that stated there was 41% of Americans that approved of the president. So P is equal to that 41%. Note that we're going to express 41% as a decimal because that's the way our calculator will want to interpret it. So we'll use a decimal for any percentages. Alternate, you want to see if your town is lower, you believe your town is less approving of the president, so you would say P is less than 0.41. So you take out your calculator and you go down to the one prop z-test. In your P0, you would type in 0.41. From your data, the number of successes you collected over here was 31 out of 90. Your proportion, your alternative hypothesis that your proportion is less than that 0.41. So again, we'd have the middle value here, and then we calculate. And what we're going to get here as our p-value is 0.103. And assuming an alpha of 0.05, that again is not going to be significant. So we are going to have data that does not reach statistical significance. Therefore, we cannot conclude that our town is statistically significantly lower. Just a reminder, whenever we reject the null hypothesis, whenever p is very small and we reject, then what we're saying is that it is statistically significant. Rejecting is good, statistically significant is good. If we fail to reject, as we did in this case, we are not going to reject, p is too high, we are not statistically significantly lower. There is not a statistically significant change if we do not reject, if p is too high.